Okay, hi everyone. So we're very happy today to have João Faria Martins from University of Leeds, who is going to tell us about Quinn Finite Total Homotopy TQFT as a once extended TQFT. João, please, it's yours.
So hello everyone. So many thanks for this invite for this talk, and it's a pleasure to see Hashem and Urs, which I hadn't seen for a decade, more or less. And I see Tim and Jack several times. So, but hello everyone. Also nice to see Sachin. Yes, I said that. Sometimes you say something which are insulting. Nice to see Sachin, sorry. Right. So let me just start. So this is actually a project that has gone on like for a few years. And so I don't know your background, so I'll go very slow in the beginning and way too fast in the end. So I'll start with describing the category of manifolds and cobordism. So anytime you're given a non-negative integer n, you can define a symmetrical category, which I'll denote cob n plus 1. So the category with objects smooth n manifolds enclosed, A, B, and morphisms from manifold A to manifold B are equivalent classes of diagrams of this form. So M is a smooth manifold, and I and J together, if I consider the universal map from the disjoint union of A to B to the partial of M, this induces a diffeomorphism. So the visualization is as it is here on the bottom left corner. And as usual, the composition of morphisms is obtained by gluing, and there's like several details to check that this is all well defined. For example, collars are required to construct smooth structure, to construct identities. It's actually, things are actually slightly more complicated than implied in the literature, but this has been worked out properly several times. And more precisely, and this is actually something I'll need later on, the composition of cobordisms is done via Pushout. So here I have cobordism from A to B. Here I have a cobordism from B to C. And I do the Pushout of M with N over B. And this is my new cobordism now from A to C. And by the way, this is a Pushout in the category of topological spaces. So this is not given a smooth structure by inception, and this actually needs to be put after. And actually that smooth structure is not unique. It's only unique up to diffeomorphism. Like I said, there are details that need check, but they've been looked at several times. And let me say, this is a symmetric monadal category, and the monadal structure is induced from disjoint union of manifolds and of cobordisms. Right, so what is a topological quantum field theory? It's now a very old definition, over 20 years old. The TQFT for non-negative integer n is a symmetric monadal functor from the category of n-dimensional manifolds and cobordism to vect, which is the symmetric monadal category of vector spaces and linear maps. Here, the monadal structure is given by the usual tensor product. I'm going a bit fast. But do ask questions. I always prefer to stop presenting slides and go back to the whiteboard, which I also have a pen tablet if needed. Right, so what is the plan of this talk? So in this talk, I'll review Quinn's finite total homotopy TQFT, where n is non-negative integer. So this functor from cob n plus 1 into vect. It's actually quite a I think this was a well-known construction back in the 90s, and it sort of was forgotten for some reason, but it's actually quite a nice construction, toy model for TQFT. And there's a parameter here, which is called R, which is what's called a homotopically finite space. It is a parameter. It's essentially for each R, I get a different topological quantum field theory. And this construction appears, for example, in these lectures on axiomatic quantum field theory by Quinn from 1995. After reviewing the Quinn finite total homotopy TQFT, I'll explain how I can combinatorially compute it. So why is it that this can be computed in finite time? And this is mainly for the case when this space R, which is my target space, is the classifying space of a homotopy finite strict omega groupoid. So this is represented by cross complex of groupoids. This is because the combinatorial construct is really considerably simpler. And this is what I hope I'll have time to speak to tell with some details, explain the construction of the once extended version of this Quinn finite total homotopy TQFT. Right, so let's start. the talk. So what is this thing of a multi-finite space? So maybe I should just say final definition of a multi-finite space, which is a bit of a mouthful. So the space X is called homotopy finite if X has finitely many components and finitely many non-trivial homotopy groups, all of which are finite. Okay, so all homotopy groups are finite. There's only a finite number of non-trivial homotopy groups, and moreover, X has only a finite number of path components. Okay. Right, and this homotopy finite space have quite a number of nice properties. And for example, actually, what's the first example of a multi-finite space? If you grab a finite group, you can consider the classifying space of that group, which is a path-connected space. Also, fundamental group of the classifying space of G is isomorphic to G, and all other homotopy groups of the classifying space of G are finite. So BG is a homotopy finite space. By the way, I didn't explain this convention, sorry. And more generally, if G is a finite groupoid or a finite two-group, then the classifying space of G is homotopy finite. So these homotopy finite spaces, which is the data that we need to construct this Quinn finite homotopy TQFT, do exist, and there are actually a number of them. And there'll be some examples sketched later. Right, so what can you do with homotopy finite spaces? You can compute a homotopy content, which is given by this Euler characteristic type formula. So you consider this infinite product where you put the cardinality of homotopy groups on the denominator and the cardinality of the even homotopy groups on top of the fraction, and then you sum over all path components. And as long as the space is homotopy finite, you get a finite, well, you get a rational number. Q, actually, you get a positive rational number. Okay, right. And for example, if G is the group, and if you compute this if you consider this classifying space, then the homotopy content of the classifying space is 1 over the, cardinality of G. And I believe the first place the homotopy content appeared was actually in these lectures by Quinn from 1995, but it has appeared in several publications because this is a formula that you very easily led to it without knowing that it's called homotopy content. So I'm sure it has been rediscovered by a plethora of people. Right, so this homotopy content is truly a nice construction. It's, for example, if X and Y are homotopy finite, then their product and their disjoint union is homotopy finite. Moreover, homotopy content is multiplicative with respect to products and additive with respect to disjoint unions. That's easy to prove. Slightly harder to prove is the fact that if P from E to B is a vibration of homotopy finite, vibration here I means Hurewicz. And if you grab an element B of the base, then first of all, the fiber is going to be homotopy finite. And this is the main powerhouse for the construction of the Quinn finite total homotopy TQFT. The homotopy content of the total space is given by the homotopy content of the base times the homotopy content of the fiber. These two results follow more or less easily from the homotopy long exact sequence of the vibration, applying some telescopic calculations, and some other details still need to be set to make it work, but it's still essentially elementary homotopy theory. And these results are, for example, these nice papers by Byers and Dolan, from finite set to Feynman diagrams, and this more recent one by Ima, Joaquin Koch, and Andrew Tonks, homotopy linear algebra from 2018. Right, so let's explain this. I still can't explain what Quinn's finite total homotopy TQFT is. So there's still something else I need to say. So, which is the following fact. So if M is a compact CW complex and R is a homotopy finite space, then the function space, so set of all functions from M to R with a compact open topology, is actually going to be a homotopy finite space. This is quite. And in particular, if M is a compact smooth manifold and R is a homotopy finite space, then the space of functions from M to R is homotopy finite, and therefore you can compute its homotopy content. Right, so I think I'm now able to say what this Quinn finite total homotopy TQFT is. Let me just maybe say a couple bits of notation. So it's more convenient to use this exponential notation for function spaces. So the space of functions from M to R will be R power M. And if I have any space X, topological space, I'll denote the path component of a little x in capital X with this notation PCX of X. Note that I want to consider the entire path component, so it becomes a topological space in its own right. Right, so how do you compute this Quinn finite total homotopy TQFT? First of all, there's another parameter, which is the S. It's slightly more flexible. So which vector space you assign to manifolds? So the space you assign, the vector space you assign to the manifold is pi0 of the function space of functions from A into R. So another way to see it is the set of homotopy classes of maps from the manifold A into my homotopy finite space R. And then I need to linearize and consider the free vector space over it. And by the way, this is a finite dimensional vector space because R was a homotopy finite space, and therefore the function space is homotopy finite, and therefore finite number of path components. And then I need what are the matrix elements which I assign to cobordisms. Maybe I should just write down the formula. So I have a function from A into R, a function from B into R. I need to say what this matrix element is, and what I'll do, I consider space of all functions from capital M into R that make this diagram commute. This turns out to be a homotopy finite space as well, because this is a fiber of a Hurwitz fibration of homotopy finite spaces. So I can safely compute its homotopy content. And yeah, that's it. And by the way, this calculation here does not depend, depends only on the homotopy class of F and F prime. There are still two normalizing factors you need to put in. I'd suggest not to think much about it. You need to look at the path component of F in the function space, compute its homotopy cardinality power S, and do the same thing for the path component of F prime in the space of functions power 1 minus S. This flexibility is important. So in Quinn's original construction, I think S was equal to 0 or to 1. But if you want to relate to Digraph-Witten, for example, I think S is 1/2, something like this. It's nice to have this flexibility, but all of the TQFTs are equivalent. There's a monoidal natural transformation connecting all of the S's. Right, so what is here to prove? Maybe I should just quickly explain the idea of why this is a functor. So if I have composable cobordisms, one from A to B, the other one from B to C, I want to prove that the vector space map you assign to the composition of cobordisms is equal to the composition of the maps I associate to the first cobordism and the second cobordism. So I don't expect people to completely follow it. I'm just going to say there are just two ideas that make this work. So first of all, if I have any submanifold of a manifold, I can consider the restriction map, function on the big space, restriction to the function on the small space. This is always going to be a fibration as long as sigma is a submanifold of W. Okay, and therefore I can apply this result to prove that the inclusion of B into this joint union is a fibration. And then there's this general fact about homotopy content of total space of fibrations, which I mentioned before, but there's a tweaking of it. So if I have any fibration of homotopy finite spaces, then the homotopy content of the total space is sum over path components of the base, and then you just do homotopy content of the fiber times homotopy content of the path component. And that's what makes it work. And apply this to the previous construction, and by miracle of nature, I don't know how Quinn devised this, things compose well, and you get a TQFT. I'd quite like to know the intuition behind it. I mean, you can check it works, but I would not be able to figure out this construction myself. Right. So, why is it that I like this TQFT? First of all, it works in all dimensions. It's quite a nice way to get toy examples of TQFTs. You don't need to worry about whether you actually get a TQFT, because, well, you have a TQFT by construction. You don't need to use any you don't need to use any combinatorial representation of the category of manifolds and cobordism. So the TQFT is there. Right, so some examples. So first of all, you can also twist Quinn TQFT by cohomology classes. And if you grab a finite group, and if R is the classifying space of G, you simply get the usual Diagraph-Witten theory. If G is a finite group, and if R is the classifying space of G, then this Quinn finite total homotopy TQFT you get from this classifying space of the two group coincides with Yetter homotopy two-type TQFT. Which Tim and I did like only half of the proof in a paper a long time ago, and probably at some time we should write down the other half of the proof. But Yetter can be seen as Quinn for classifying space of the two group. But what I would like to say is all of these homotopy theoretical constructions seem completely uncomputable, but all of these TQFTs, they're easy to compute. You can compute in the computer, and a lot of times you can actually compute them by hand. And this computability of Quinn homotopy, Quinn finite total homotopy TQFT generalizes.
So, sorry, before that, can I ask a question, please?
Yeah.
Yes, so I had a simple question from earlier. What's the role of that complex number S? Is it given to us, or is it something we discover?
The parameter.
It's a parameter.
For each parameter, you get a different TQFT, but they all isomorphic or naturally isomorphic. Okay, it's useful. So Quinn's original construction was for S equals 0 or S equals 1. I don't quite remember. Diagraph-Witten, I think, is S equals a half, and Yetter definitely S equals 1/2. It's just essentially a one primitive family of normalizations that make things work.
I see. Okay, thank you.
It's very easy to see. So if you try to prove that that matrix element of Quinn finite total homotopy TQFT compose well, you'll see that it's natural to consider these factors here. Yes. I'll give you the slides, and you can actually put the slides online. Okay, it works beautifully. What I was saying is that I have no idea how Quinn devised it, invented this, because I can prove it works, but I'll not be able to get it myself. Right, so let me say, so this computability in finite term of Quinn finite total homotopy TQFT generalizes. So there's this beautiful theorem of Alice, which says that any connected homotopy finite space is homotopic to space of the form W bar of G. So you have a finite simplicial group, you compute W bar, do the classifying space, and you parameterize all homotopy types of space which are homotopy, and you parameterize all homotopy types of spaces which are homotopy finite. And this is paper by Graham Ellis, space with finitely many non-zero homotopy groups, all of which are finite. And for this reason, instead of computing Quinn finite total homotopy TQFT from the point of view of topological space, you can, for example, pass to any combinatorial model for homotopy theory, for example, simplicial sets, and actually explicitly compute Quinn finite total homotopy TQFT, at least in principle. Can be like exponentially harder as the dimension of the manifolds increases, or the complexity of the homotopy of the space R increases. But the point is that Quinn TQFT is computable in finite time. So it doesn't appear to be a combinatorial construction, but actually it's the combinatorial construction, it makes sense to look at it in a bit more detail. Right, and for the remainder of this talk, I will mainly work with the case when R is the classifying space of a omega groupoid. In fact, I probably should have added strict to it. This is strict omega groupoids as defined by Broad and Higgins, and this is equivalent to a cross complex. And for example, R is can be the classifying space of a two group. And as I said before, in this case, the computation of Quinn finite total homotopy TQFT is particularly simple. Let me just put this warning: cross complexes do not model all homotopy types. So to actually get all Quinn, you need to use more sophisticated models for homotopy theory. But let us stay today with classifying spaces of omega groupoids. So let me say, for example, spaces modeled by cross complexes, for instance, have trivial Whitehead product. So they definitely don't parameterize all homotopy types by looking at cross complexes. And they haven't even defined what a cross complex is. Oh dear. So let's start with the cross module. So what's a cross module? So a cross module of groups, so is given by, first of all, a group homomorphism, partial from E to G. So E and G are part of the data. And then you have a left action of G on E by automorphisms. And then two very sensible relations must be satisfied. I'll go a bit faster here because it's a bit I want to show the principle of how things work. But this is the definition of a cross module, which, as you see, is a completely algebraic definition. And there's this old theorem by Whitehead and McLean that says that the homotopy category of cross modules is equivalent to the homotopy category of pointed two types, pointed spaces whose homotopy groups vanish if I greater than 3. And that's the reason if you just want to inspect Quinn TQFTs with classifying space or whose space R is a two type, you can just stay with spaces which are classifying spaces of cross modules. There's a minor generalization of a cross module, which is a cross complex. I'm just going to put here how a cross complex looks like. So you start with a cross module, E mapping to G, and then you add a tail to it. Okay, and several properties must hold. For example, all of these groups CI should be abelian. G must act on all the groups CI. This should say groups, not groupoids. Boundary mass preserve action. Some other conditions must be satisfied. And let also say that both of these notions, cross module and cross complexes, extend easily to the groupoid setting, which was actually the setting I had written it in the previous talk, and I didn't finish converting it, as you can see. Okay, right. So cross complexes, okay, they're a toy model for homotopy theory, but they're still, it's quite a nice model, even though it doesn't see all homotopy types. So, for example, the category of cross complex is a monodal closed category. So given two cross complexes, you can form the transfer product. Given two cross complexes, you can form the function space of cross complex maps from A to B, one-fold homotopies, two-fold homotopies, etc. And we have a natural equivalent. It's actually quite a nice category to work with. And for me, let me just say what type of monsters you get. So if G and H are finite groups seen as cross complexes, their tensor product seen as a cross complex is simply the free product, G star A, and the space of cross complex maps from G to H is a groupoid whose objects are the group maps from G to H, and whose morphisms are, well, ways to conjugate one homomorphism into another homomorphism. So the general case of this CRS GH, where G and H is a cross complex, is more or less like this, but with several other things to check. So it's actually a glorious construction, this monodal closed structure in the category of cross complexes. And if you look at the construction of it, you see how glorious construction it is. Right, so before I go to more combinatorics, let me say that you can compute the fundamental cross-complex of a CW complex. And just kind of right here, if you have a CW complex, you can construct a cross-complex out of it. So you start with a fundamental groupoid of the one skeleton on the set of 0 cells. This is actually a cross-complex of groupoids because you might have more than one cell. Then you look at relative homotopy groups and you keep on putting these relative homotopy groups. And a nice property is that it's a totally free cross-complex of groupoids. So it's as free as a cross-complex can be. So it's very easy to define maps from the fundamental cross-complex of a CW complex into any other cross-complex, as long as you know how the cells of the CW complex attach. By the way, this is an old construction. So this totally free cross-complex is due to Brown-Higgins, but the fact that this is cross-complex is actually, I think it's in Whitehead's original paper on CW complexes. So it's again, very old homotopy theoretical technology. Right, and what else can you do with cross-complexes? You can compute their class. You can consider classifying spaces. So if you have a cross-complex, you can consider the nerve. It's going to be very fast, but let's say it's a simplicial set whose end simplices consists of cross-complex maps from the fundamental cross-complex of the end simplex E to C. And the classifying space is simply given by the geometric realization of the nerve. And if you grab a group, you get the exact classifying space of the group. If you grab a cross module, you get exactly the usual classifying space of a cross module. I can discuss this later on today, but maybe I would like to just say the principle. There's another principle which are important, which is the homotopy groups of the classifying space of the cross complex turn now to coincide up to isomorphism with the homology groups of the cross complex. So if you start with a finite cross complex, then you immediately get a homotopy finite space by looking at the classifying space. Right, and what comes after? So let's then explain how to compute this Quinn finite total homotopy TQFT for R, the classifying space of a CW complex. So see a homotopically finite cross complex. Actually, I think it should be finite here. I'll see. And so there's this theorem. If A is a closed manifold, is a closed N manifold with a triangulation, then the space, the vector space that Quinn TQFT with the classifying space of C associates to A turns out to be the free vector space on pi 0 of this cross complex. Here we call this C power pi of AT is the internal Hom in the category of cross complexes. So let me spell this out what this means, since this notation can be tricky. So this is a space, the vector space whose basis consists of all cross complex morphisms from the fundamental cross module, fundamental cross complex width of A with that triangulation. Looking at the fact that the triangulation gives rise to a CW complex structure, and you consider these maps up to homotopy or pseudo-natural equivalents. So say homotopy if you think of cross complexes, say pseudo-natural equivalents if you think of omega groupoids. The two settings are mutually convertible one into the other. So the vector space associated to manifolds are completely determined because this fundamental cross module of A with the triangulation can be presented by generators and relations. So I can explicitly compute with this cross complex. And it's actually finite as long as C is finite. And can also compute the matrix elements. So if you have a cobordism, you can consider triangulation of the big manifold, extend the triangulations of the manifold A and the manifold B. And maybe I should just say, so what's the actual formula for the matrix elements? So you have a certain cross complex map from fundamental cross complex of AT into the cross complex. You have a cross complex map from here to here. You consider the set of all cross complex maps that extend F and F prime, and you compute its cardinality. And I'm going to say compute its cardinality. You're looking at it as a set, not as a vector space, or not as a topological space. So there's no need here to compute that infinite product of the cardinalities of the homotopy groups. It's really simply cardinality of a set, which can be computed with the hands, and then there are factors that you need to multiply, but there are factors that depend only on the number of simplices of the manifolds and on the cross complex. So for example, a factor could be number of vertices of M, a factor could be cardinality of the group G power number of vertices of the manifolds, something like this. So something which is universal for all cases. This is actually the big simplification that happens for the case of classifying spaces of cross complexes. It might also be the case for general simplicial groups, but I do not know. Maybe at some point I should be looking at it. Right, any questions? I think the next page is already about the extension of Quinn TQFT. No questions?
Maybe can I ask a question? Could you maybe say what we kind of learned from this CQFT? Is it just kind of an exercise in constructing one, or is there something what did Quinn make of it? Is it something we encounter in nature, or
toy model? Toy model, yes, but it turns out to give several examples of TQFT, and it works in all dimensions, and it's explicitly computable. And well, it's a TQFT for higher gauge theory if you work with a cross complex. So it's a natural generalization of Digraph-Witten theory, where instead of working with a group of coefficients, you look at a homotopy finite space of coefficients. So I look at it a bit like this, but we are not going to be able to distinguish smooth structure with Quinn TQFT because the construction is just a topological construction. There's no way the smooth structures are embedded here.
Maybe another question, is the restriction to cross complexes one of convenience, or is it actually crucial for the definition?
No, this works for any homotopy finite space. This calculation here, which is so simple, we only know it works for classifying space of cross complexes. But Quinn finite total homotopy TQFT, it works for any space P or R. The issue that computing it will be a bit more complicated in theory. But we could work with classifying space of two cross modules, for example, but then maybe this formula would not be as simple. You need to put more stuff.
But what is it about this formula that is crossed? I mean, it's just, it seems to have an immediate generalization. Or what is it? Let's see, where in this formula are you using cross-complex structure, like crucially?
Where it's used, well, there's a space, there's a step to construct this formula, which is an Allenberg-Silber theorem, which permits to completely assess. I didn't write it down here. I can discuss this after, but this theorem here depends on an Allenberg-Silber theorem, which permits a really simple construction of the simplicial set of maps from M into the nerve of C. And I'm only aware of such a formula existing for crossed complexes. So this depends on a result of Tongs, which is the Allenberg-Silber theorem for cross complexes. So all of the rest of Quinn's TQFT works, but this step here, as far as I can prove, only works for cross complexes. Maybe it works in other settings. I just don't know the proof. Did I answer your question, Urs?
Thanks. Yes.
That's a good point. This should be clarified. So this depends theorem for cross complexes, which is already a non-abelian generalization, which is already quite a glorious result, I can tell you. Right, so let's now finally get to extended Quinn. So start with the bicategory of manifolds, cobordisms, and extended cobordisms. So I'm ordinate by cob n+1, n+2. So objects are n-dimensional porous manifolds. One morphisms are cobordisms from A to B, and two morphisms will be extended cobordisms, things that look more or less like this. So this would be an extended cobordism from the cobordism M from A to B to the cobordism N from A into B. And these things compose horizontally and vertically. And you need to give several details, especially about the smooth structure and lots of things. So this is nowhere near as simple as I'm making it, but as in other cases, people have looked at it in detail. So you do get a bicategory, actually a symmetric monoidal bicategory of manifolds, cobordisms, and extended cobordisms. And I'd like to look at once extended TQFTs and simply define a once extended TQFT as a symmetric monoidal bifunctor from the bicategory of n manifolds, n+1 cobordisms, and n+2 extended cobordisms to Alsch. And Alsch is some algebraically defined symmetric monoidal bicategory. And which bicategories would I like to consider as Alsch? So targets for these symmetric monoidal bifunctors can. The first idea that comes to mind is the bicategory more. So the Morita bicategory. So objects are algebras, when morphisms are bimodules, and the composition of bimodules is given by the usual, well, tensor product of bimodules over the middle algebra. And two morphisms are bimodule maps. So this is a very nice construction of a symmetric monoidal bicategory. In fact, this is probably one of the constructions that motivated Benabu to construct, to start a theory of bicategories. And another more practical construction is profunctors or distributors or modules, depending on the school. So version of the bicategory of profunctor work here today. Objects are homotopy finite groupoids. One morphisms from G to H are functors from G up times H into vects. And the composition of these profunctors is given by the usual profunctor composition, i.e. via coens, and two morphisms are natural transformations of functors. So these are two very well established examples of symmetric monoidal bicategories, and I'd like to look at these as the main target. And as you'll see later on today, very quickly, there's a linearization functor from prof into more, which is sort of take the obvious linearization, check a few details, but it works properly. In fact, this is in our recent paper with Tim. Right, so I would like to consider an extended version of Quinn finite total homotopy TQFT. And I'll start by saying what the Homotopy Powerhouse for it is. And for the for Quinn finite total homotopy TQFT, the powerhouse was the fact that the homotopy content of the total space of a fibration is equal to the homotopy content of the base times homotopy content of the fiber. Here I need to look at other type of results. So let top be the category of spaces and homotopy classes of maps. There's this classical result which says that if you have a fibration, a Eurythmics fibration, then immediately we have a functor from the fundamental groupoid of the base into the category of topological spaces and homotopy classes of maps. And what does it do? It sends every point of the base to the fiber. And right, and it's a bit trickier to define the functor on objects, i.e. paths. Let me say it's obtained by applying the homotopy lifting property to the path gamma and just looking at some obvious commutative diagram. Okay, and I call it all because this, if you have a fiber bundle, this can be realized by putting a connection on the fiber bundle. and you get a version of this all. Okay. Right, so just trust me. So if you have a fibration, then you have a functor from the fundamental group ordered manifold into top. So sends an object to the fiber. And if I have a map between points on the base, there's a natural map that you can construct from fiber of X to fiber of Y, given the homotopy lifting property, or think of it as the usual parallel transport by picking a connection. Okay, so this is the homotopic powerhouse, actually the first of them. There are a few other, but that's the only one I'll mention today. And main theorem, let R be a homotopy finite space, so doesn't need to be the classifying space of the cross complex. Then we have a once extended TQFT from cob n, n+1, n+2 to prof. And what does it do? You send an n manifold to the homotopy groupoid, to the fundamental groupoid of the function space of maps from A into R, my space of coefficients. And now I need to say what I do to cobordism. And I'm going to go very quickly. So anytime I have a cobordism, I can consider the path space fibration. So a function defined on M restricts to a function defined on A and B. And if I have a fibration, I have a functor, and essentially the proof functor is obtained by playing a bit with this functor. There's a composition of these things. So you first look at the fundamental groupoids of these function spaces, apply the holonomy functor, apply pi0 to go from spaces and homotopy class of maps to sets and maps between sets, and then linearize to apply to vector. By the way, this pi0 is a place where a lot of information is being lost. And I'm sure it's actually possible to get final results, maybe not today. And from here, this extended Quinn is more or less like Quinn TQFT, but there's several things to check. It took a year to check all the details that it works. Well, it was the year of COVID, so there's excuses. Right, so this is our proposal for this extended Quinn TQFT, and let me now convince you that this can be computed, and you can actually do calculations with it. And first of all, you will observe that if R is a multi-finite space, then the vector space actually groupoid that the extended Quinn associates to the manifold is uncountable, because the fundamental groupoid of the function space, so you have one object of the groupoid for each element of the function space. And so first of all, we need to figure out a way to reduce the size of the target groupoids. And there's a bit of a non-natural thing I'm now going to need to do. And let me start with the definition of the decorated manifold. So if R is a multi-finite space, decorated manifold is essentially you have a manifold and then you choose a finite subset of the function space that contains at least one element for each homotopy class of maps from A into R. Okay, it's always possible to do this because this R power A is a homotopy finite space, so it has a finite number of path components. And then you have this tweaking of the bicategory of manifolds, cobordism and extended cobordisms, where instead of picking manifolds, I pick decorated manifolds. So I pick a choice of base points for the function space for each R finite. Right, and from the previous results, if R is a multi-finite space and n is a non-negative integer, we have this finite reversion of the once extended Quinn TQFT. So it goes from this bicategory of decorated manifolds, cobordisms and extended cobordisms to prof. And essentially it sends a decorated manifold to the fundamental groupoid of the function space based on this finite set. And in doing so, we realize the next step in which you make these target groupoids finite. Okay, and of course, if you change the decoration of the manifolds, you change the groupoids, but if you pick different decoration of the manifold, there's a canonical profunctor connecting them, and this satisfies all properties you want it to satisfy. So this is a natural way to pass from the groupoid associated to a decoration to the groupoid associated to another decoration. And I didn't write down we didn't write down the relations properly, but there's a natural way to go from one into the other. But if you pass to the Morita version, this is actually just says that there is a natural Morita equivalent between the algebras associated to one decoration and the algebras associated to another decoration. Right. So and now what is this Morita value? So there's yet another symmetric model by functor from this bicategory of decorated manifolds, cobordisms, and extended cobordisms. Oh, sorry, I'd forgotten the way I had stated this. What I want to say is that this initial unitary version of the Quinn finite Homotopy TQFT can be linearized. So essentially, you start with the groupoids, and you convert it into an algebra by considering its groupoid algebra. And anytime you have a profunctor, you transform it into a bimodule. Some details must be checked, but indeed, you can easily pass from bicategories of profunctors to the Morita bicategory. Right, and this is our proposition or our proposal for this Morita valued extended Quinn TQFT. And okay, this all works for all dimensions, for all spaces, but you must argue these things are computable and not just abstract constructions. And again, homotopy groups of function spaces can always be computed in principle, for example, by passing to simplicial sets and simplicial groups. Things become particularly simple in the case of strict omega groupoids, again, because this Eilenberg-Zilber theorem for cross complexes. And I'm going to be a bit quicker. So suppose now that this space of coefficients is classifying space of a finite cross complex, then anytime you give a triangulation of the manifold, this gives naturally a way to put base points in the function spaces. And what makes this extended TQFTs computable is this result here, which is that the groupoids that extended Quinn associates with triangulated manifold are actually the fundamental groupoid of the internal home in the category of cross complexes. So, and then you go from the profunctor case to Morita just by linearizing. So maybe I should explain what this is. I can give more details later on. So what is the groupoid you associate to a triangulated manifold? The groupoid of cross-complex morphisms from fundamental cross-complex with triangulation into C, and morphisms between morphisms, so this is an internal home, are twofold homotopy classes of homotopies between cross-complex maps. And therefore, these once extended TQFTs can be computed in principle, because pi of AT, which is what you have here, is fundamental cross complex of a finite CW complex. It's a totally free finite cross complex, and C is a finite CW complex. So you can do calculations with the hands. You don't even need to put it in a computer. So, right. So you probably also noticed here that there's this triangulation dependence, but the triangulation dependence only happens at lower dimension, at dimension n. Okay, so you don't have any triangulations on the cobordisms and extended cobordisms. I look at it as a flexibility. So if you choose, you're free to choose an n manifold with the triangulation you want, and that gives an algebra. Right. Let me just quickly explain how this gives rise to what people usually call extended TQFTs and some choices. So you need to pick a set containing at least one representative of each diffeomorphism class of closed connected N manifolds. Choose a triangulation of each of these manifolds, AI, and I'm not going to say the main theorem, but the theorem that may be stated in a language is more common. So anytime I have a positive integer, I have once extended TQFTs from COB n plus 1, n plus 2 into more, and also into prof. Oh dear, these are swept. Should be profunctors and Morita by category. And is the rule. So what is the algebra? And profunctor you associate to a manifold. So again, compute the fundamental cross complex of the triangulated manifold, do the internal hom of maps to the cross complex C, and look at the fundamental groupoid of that cross complex. Everything is finite. In the Morita case, just linearize and pass from a groupoid to a groupoid algebra. And by the way, so if you change these triangulations on the manifold, there are canonical Morita equivalences between the algebras thereby constructed. It's not that the algebras are Morita equivalent, it's that there are canonical Morita contexts between the algebras, which is a lot stronger. Okay, and this is a result by Alex Bullivant, and this is essentially in his PhD thesis in Leeds some time ago, but this is research of PhD that sparked a lot of this research. Right, so examples. Quickly time for examples, and I'm going to take the simplest possible case because I have too much abstraction. So let's look at the case of G, a finite group, which we can always convert to a cross complex. Everything is trivial beyond dimension 0. So if n is equal to 0, so n is the, okay, let me just go back to here. So for any n, we have a once extended TQFT. So the n here denotes the dimension of the manifolds. Okay, so if n is equal to 0, then the groupoid that this extended Quinn associates to a point is G. Well, it could only be G, of course, by the no-Freelanch theorem. So the algebra associated to a point is the group algebra of G. And slightly more complicated example. So for n equals 1, so the profunctor, actually the groupoid associated to S1 with the simplest triangulation is the conjugation groupoid of G. So objects are elements of G, morphisms are a way to conjugate one element to the other. So when you linearize, you simply get the quantum double of CG. So everything is working. So this is actually a new proof that we have a 1 to 3x in TQFT sending S1 to the quantum double of G, which is a result by Jeffrey Morton. And from here, because it's just a group, things become slightly less interesting. So the groupoid, the algebra associated to S2 is C. The algebra associated to the torus is the groupoid algebra of the action groupoid. So space of things commuting in G times G over conjugation by G. And okay, this is the absolutely simplest case. I mean, this construction works for any cross complex. In fact, it should work for any simplicial group. Well, it does, but the formula might be a bit more complicated. And let me just look at the higher case. So if you look at the finite cross module, the groupoid associated to S1 as objects, elements of G, and morphisms are equivalence classes of arrows like this. So want to think about our gauge theory, the groupoid you associate to S1 is the groupoid of G2 connections in S1, and morphisms are equivalence classes of gauge transformations up to gauge transformations. And let me say, these two algebras appeared in these beautiful papers by Alex Bullivant and Clemens Delkamp. And this is a Homotopy theoretical interpretation of the tube algebras, which they use to look at excitation statistics for 2+ dimensional topological phases derived from higher gauge theory. I think the talk is finished. I'm very happy to answer any questions. I went faster probably than I should. And well, examples were very trivial, but the framework is considerably more general. Lots more things can be done with it. So thanks. So everything is on the internet. So this is the first paper with Tim, 2007, and 16 years later, with thousands of Skype meetings, now Zoom, we finally managed to do paper 2 in 2023.
Thank you very much. Thank you. Okay, any further questions for João?
Can I maybe ask one question?
Go ahead.
Yes, of course.
This may just show that I didn't pay full attention, but could you just say, do you recover Quinn's original construction as a decategorification of your new one, or is it?
Yes, by inception, yes.
So it actually,
And also,
it actually is an extension.
So you would go from the fundamental groupoid of the function space to pi0 of the function space. So if you look at fundamental groupoids as a categorification of pi0, then yes.
Right,
Sorry,
but
I think
what I mean is, okay, like, is there a forgetful functor from your once extended TQFT to ordinary TQFTs that maps your once extended construction back to Quinn's?
I never thought about it. It's an it's a categorification, well, interpreted like in a loose way. It's a sensible way to make the construction categorical, but I didn't really write down the full details. Maybe the forgetful functor. So if you consider n+1 cobordisms from empty to empty,
Yes.
and extended cobordisms from this type of cobordisms to itself, then extended Quinn is exactly Quinn.
Okay, thanks.
Perhaps with some factors being added and some nitty-gritty details, but this is essentially what I wrote here. So once you, sorry, last time I do this because it can be annoying. So once you get to extended cobordisms, you do exactly the Quinn's construction. In particular, if this manifold A is empty and this manifold B is empty, so you're actually back to the construction, back to the notion of cobordisms, back to the notion of manifolds and cobordisms, then you get exactly Quinn TQFT. Exactly, maybe with some factors being added. But I don't know any more functorial realizations. This paper was example-based. I wanted to give several examples of extended TQFTs that exist in all dimensions, and they are computable. This is the ultimate digraph with an extended TQFT, so to speak. I think it can be more categorified.
okay. So actually I have a question. So you reproduce these examples, which is very nice. And now, is there a sense in which this approach that you use will allow for more computability or lack of? I mean, is there some insights that are introduced into the examples you could reproduce, let's say?
I could not understand your question because you broke in the middle.
Oh,
of the
sorry.
sentence.
I was asking, it's nice that you reproduce these examples, but you're using this approach. Is there any sense in which this approach will help allow us to have more handle on these examples that you reproduce, for instance, computability or other?
I think it's more of a sandpit for how higher DQFTs would look like in all dimensions. It's example driven.
Right.
You give me an N type, I give you a TQFT and an extended TQFT that can be computed. It's
I see.
more examples driven.
Computed, right? Yeah.
Yeah, can in theory be computed, but yes, this is examples driven. If you see what I mean, it's a good question. Yeah,
Oh yeah,
should
yeah, that's nice.
look at it, and believe me, the details took completely over for years. So
Really
happy
appreciate.
to.
Yes.
We have this paper actually is 270 pages, and it's trained energies year after year.
Oh wow. Okay.
Tim and myself. But then the formulae are simple. The hard thing is to prove that they work. So, which
Great. Excellent work.
be that. Yep.
Other questions? Okay, great. Let's thank João again for the very nice talk. Thank you very much.
Nice to see everyone.
Yeah, nice to see you, everyone.
Bye.
Hi, Tim, and I hope to see you guys somewhere in some conference.
Yes, we hope to meet in the near future. And yeah, thank